Hello everyone and welcome back to the Victoria Game Engine series. This is episode 12 and today we're going to be making a triangle appear onto our screens. So today's episode is going to be fairly temporary in terms of the actual code that we write, but this is mostly going to be a demonstration of the fact that we can now do this properly. So all of our code is now going to be going inside of our main.cpp file for this episode, and we're going to need to create a few things up here before we actually start doing anything lower down. So the first thing that we're going to be doing is we're going to be creating a struct to hold all of our data that we need for our OpenGL functions. So I'm going to go enter down here and we're going to call it struct GL context. Please note that this isn't the same as an actual OpenGL context as we've been over in previous videos, but this mainly exists as a struct name just so that we can keep our data. So we're going to call it struct context. Or GL context, I should say, or just context itself. And we're going to have a couple of things in here. The first thing we're going to have is we're going to have a GL uint shader program. We're going to have GL uint vertex array, GL uint vertex buffer. We will be coming back and adding a couple of things up at the top here as we go through the video, but I'll try to get back to those when they are most relevant. The first part of our code here is actually going to involve getting a little bit of information, because the way that we run OpenGL, often what you need to do is you need to first off create some shaders, and we'll be creating those shaders in a moment. Once you've created those shaders, you then need to link them to a shader program, which can then use those different stages to compile them, link them together, and then you have effectively how you're going to output your object. Once you've done that, you're then going to want to get some vertex information, throw that into an object that OpenGL can store, and then when you need to, when we're doing our iteration loops, it can then draw that on the screen. Now, that was a very basic overview, but we are going to explain it first by writing our shaders. Up here, we're going to declare a const char vertex shader source, and it's going to equal some stuff that I'm writing here. And then from there, we're going to just paste because it's going to take forever to type out otherwise. And here we are. You can get rid of the spaces in between. Those are just because of how those were just formatting problems. And here we have our very first shader. We've not created it in a file yet because we don't have any way to load them, but we'll be getting to that point soon. So the way this works is in every OpenGL shader, you may know GLSL shaders, there are a few things that you need to define. The first one is the version of OpenGL that you're using. Here I've declared version 460 because we're using OpenGL version 4.6. Then we want to declare some information about the data that we're sending in. So here we've said layout location equals 0 in vec3 apos. In essence, what this means is that at the first location binding, we are going to be inputting a bunch of vector 3s and this will represent position. And then in the shader's main function, we then call to GL position, which is a global variable that just means the position of this vertex. And we create a vector 4 with the X, Y, and Z actually specified, and then 1.0 for the W component. Another important thing to note about a lot of OpenGL shaders is that they will run per whatever that you're defining. So here, this shader runs for every vertex that you want to draw. Every time that you specify a vertex in an array, the vertex shader will be called, and this will define some information about that vertex. The fragment shader, which we're about to write as well, runs for every fragment, which is also known as every single pixel on your screen for which the object is visible. Speaking of which, here it comes. Again, going to get rid of the weird spacing, but I will do my best to explain. So here the fragment shader is slightly different. The first thing it declares is the same, But here we declare an outvec for our fragment color instead of an invec for. This is because OpenGL does not provide a GL frag color like it does here. It instead wants you to output a color, and any default color that is selected as your output is whatever it's going to display for that fragment. And we just make it specific to this color variable here. These are our RGB values, and this is our alpha value. And that's all this shader does. So again, fairly simple, but when we get into the logistics of shaders, this will be a concept that will get run up and again. So it's a good idea to get an idea of how these work right now. However, with that out of the way, we can now go back to our start loop and we can actually start writing things. First thing we're going to call is we're going to call a GL vertex shader. And we're going to call to GL create shader. I'm going to call GL vertex shader. The way a lot of OpenGL programs work is they create objects that exist on the GPU, and you access these objects by its ID. Now here, because we're only going to need the vertex shader very briefly when we're actually setting up our shader program, we're declaring it here rather than in our struct because it doesn't need to be accessed once we've done all of the compilation. Speaking of which, we're now going to call to GL shader source for our vertex shader. We're going to pass 1 as the number of shaders we're trying to fix. We're going to pass 1 as the number of strings we're passing in. We're going to pass the memory address of the vertex shader source, and we're going to pass null pointer here for the length of the shader. Because we have specified our null terminator, we know how long each shader is going to be. And then from here, we call to GL compile shader using the vertex shader. And that will mean that the shader gets translated into binary, which can be read by the GPU. Now, in case anything has gone wrong at this stage, it is a very good idea to call to the OpenGL API and see if anything has gone wrong. So here, we're going to declare an integer called success. I'm going to declare a char array called info log. I'm going to make it 512 bytes long. I'm going to call GL get shader IV, the vertex shader, GL compile status. I'm going to pass the address of success. And what that's going to do is going to determine if success has passed or not. And if it hasn't, then we need to print an error. So if not success, then it's called GL get shader info log context, or just vertex shader 512 null, or null pointer I should specify, and the info log. Then we call to our OS get singleton print error info log. And we're going to be repeating this process again for whenever we're doing anything with shaders, just so that we know if everything's going all right. Now, to create another GL uint, and we're going to call this fragment shader. And it's going to follow the same type of setup. GL create shader, GL fragment shader. GL shader source. Which again has been camel cased, so if you want to change that back, you can. I am personally going to be doing that because the code that I used is a little bit inconsistent in that manner. And then we're going to pass null pointer here as well. Then again, call to compile the shader. Now, again, if this has faced any errors, then we're going to want to double check that. So GL get shader IV, call on the fragment shader, gl compile status and success. If success has failed, we're going to do gl get shader info log, fragment shader, 512, null pointer, info log, and os get singleton, print error, info log. Later on in our project, we will be making this into a function because you'll want to call it every time you compile a shader. But at the moment, we're only trying to compile them as soon as possible, so we do it this way. And now at this point, we've gotten the two main shaders that you'll always need in any OpenGL project. That is your vertex shader and your fragment shader. There are other shaders that exist. There are geometry shaders, tessellation shaders, and a whole bunch of other shaders that I really don't quite understand that we won't be touching on for this tutorial, because this tutorial is primarily just going to be focusing on the absolute basics. Anyway, at this point now, we have set up our vertex and fragment shader, and we're finally ready to create our shader program. A shader program is a shared object that, when it is bound by the OpenGL API, will cause every time you do a draw operation on a specific object, it will draw that buffer of data to the screen in whatever format you specify. And this is powerful because you don't need to create a shader for every object that exists in your scene. You only need to create a shader for every object type that exists, and some specialized versions when we get to that, which is going to be in the very far future, because my ahead of time implementations of a lot of stuff for this series haven't even got to the point of doing custom shaders yet. Anyway, here we're going to want to create that shader program. So we're going to call context.shaderProgram equals gl create program. Doesn't require anything. It just wants a program to be created. Once you've done that, you're going to want to call to attach shader program, or gl attach shader, I should say. And this will attach all the different shaders that exist in our pipeline setup to the shader program. So context.shaderProgram, vertex shader, and call again for the fragment shader. So context.shaderProgram, fragment shader. And then from there, you're going to call to gl link program. This is because in our vertex shader, you can specify out attributes, which are things that will be spit out from the vertex shader that you'll then want to input into your fragment shader. These are often useful because sometimes you'll want to specify normal data in the vertex shader, but the vertex shader often doesn't use normal data. It's actually the fragment shader that cares more about it for stuff like lighting information. So passing the two through requires that they are linked in some way, and that is the point of the shader program here. And as you can imagine, we're going to want to again call to get program IV, because we're going to want to double check that this linking step hasn't happened, or this linking step has happened, I should say. As otherwise there are linker errors that you can get. They're not as easy to cause as compilation errors in these stages, but they can happen. And here, if success, of course, has failed, then we're going to want to get a program info log. So from our context.shaderProgram, 512, null pointer, info log, and print to the here whatever information that is wrong. Now at this point, we're pretty much done with our vertex and fragment shaders, so we can just call gl delete shader on them to our vertex shader and to our fragment shader. Normally, this seems like a bad idea to do something like this, since the vertex and fragment shaders are still going to be used by the program. But because they've been compiled and linked with our shader program, they exist on the GPU side, and therefore we don't need to keep hold of any of these objects once we're done with them. So at this point, it's safe to destroy them and then move on with our lives. Next up is actually specifying the vertex information. This is where it gets fun. So at the moment, we don't actually have any information about our screen defined. We're not even using any of the maths that normally goes behind a lot of this stuff. We are just focusing on raw OpenGL information. So what that means is that when we specify the coordinates for geometry, we don't have a way to specify in a world space. We are just going to be using screen space coordinates. You can imagine these like the center of your screen being 0, 0. The bottom left is -1, -1, and the top right is 1, 1. These are what we call normalized device coordinates, and pretty much every single shader program that you'll use, or every single shader that we write, eventually translates your vertex information from local coordinates to world coordinates to camera space coordinates to a projection matrix, eventually to normalized device coordinates. Now that pipeline is something that we are going to deal with a little bit later in the series, but for now we are just going to write some normalized device coordinate spaces because none of that information has been specified. So that means is we're going to write an array of floats, so we're going to call it float vertices. You can specify 9 here, you don't have to. The compiler is smart enough. And the vertices are going to be as follows: -0.5f, -0.5f, 0.0f. So again, that's the bottom left. That's halfway between the center and the bottom left of the screen. 0.5f, -0.5f, 0.0f. So that's the bottom right of your screen. Then 0.0f, 0.5f, 0.0f. And that would be the top middle, sort of where my cursor is right now. And with this information, we need to now pass this into a couple of objects. There are two main objects that we're going to be using here. There is a vertex array object and a vertex buffer object. The two can sound very similar, but they actually serve very different purposes. The first one is a vertex buffer object, or as its internal type is, a GL array buffer, effectively acts as it would sound, an array of data that exists on your GPU. A vertex array object is effectively a manager for your vertex buffer. So whenever we do read-write operations with our vertex buffer, we always need to have a bound vertex array because all of the information relates to that specific vertex array whenever we are doing any form of adding data to it, removing data to it, modifying data. If we want to draw an object with these vertices, we have to make sure that we bind a vertex buffer to it and perform all of our read-write operations to that buffer with it attached. If that doesn't make any sense, I will try my best to explain it through the code that we're about to write. So the first thing we call to is GL gen vertex arrays. Again, we only want one vertex array, and we're going to call to context.vertexArray. Then to call to GL gen buffers, one context.vertexBuffer. As you can imagine, both of these, all they do is they create a vertex array object that is assigned to this particular integer, and the same thing for this vertex buffer as well. Now we want to bind the vertex array. So once we've bound this vertex array, well, we're going to need a vertex buffer for it to read all of its information from. So we call to GL bind buffer, GL array buffer, and we call to the context.vertexBuffer itself. It doesn't matter that we generated the vertex buffer outside of the binding of the vertex array. It just matters that we bind the buffer to the array here. And now we need to upload some data to the GPU. So the way we could do this is we call to GL buffer data, GL array buffer, size of vertices, vertices themselves, GL static draw. And what this does is effectively it says that the current buffer that we're dealing with, which is an array buffer, We want all of the data from this array, which can be cast as a void pointer, so you can have a void pointer of vertices, uploaded to the GPU, and this is how many vertices it should read from that buffer. Again, you can have sometimes a vertex buffer can go over, so this could be, say, 18 bytes long and not have all that information initialized. We only want the first 9 instances within this array. And then we call to GL static draw to let the GPU know that this information is unlikely to be swapped and changed at any point, because we are only ever going to be dealing with this one pass of adding information to it. There will be a later point in the series where we call to GL buffer data and its cousin GL buffer subdata when we are using dynamic draw or stream draw, and this is when data can change throughout the lifetime of an object, often when you're dealing with material data, as I said before. But for now, we don't need to worry about that. And down here, we're going to call to GL vertex attrib pointer. And what this is going to do is we are effectively trying to enable an attribute array. If you remember up here, this layout location equals 0, this refers to an attribute array. Effectively, for every piece of data that exists in this vertex buffer, some of this data needs to be assigned to this attribute array in some way so that we can actually define vertices using this method. And of course, this is bound to attribute number 0. Because we're dealing with a vec3, we're going to specify 3 elements. The actual data we're dealing with here is a float, so we're going to call to GL float. If the data needs to be normalized, i.e. does it need to be capped between a range of 0 and 1, in our context, we do not want that to happen, so we call to GL false. The stride refers to how far within the array is it between each data point we're trying to assign. So for instance, if you're dealing with having vertex data, color data, normal data, and UV data, for instance, you will need to increase the stride from the current point that your data is at to where that next data is held through whatever algorithm you decide. But here, all we need to do is 3 times size of float. Because fortunately enough for us, we are only dealing with one data type so far. And effectively what that will do is that means that every time it wants to read in a vector3 for position data, it will look, okay, here's the first 3 elements. Then we're going to move down here to the next 3 elements. Then we're going to move down here to the next 3 elements. And of course, if you are actually dealing with a large array and you have multiple data types within it, you often need to implement whenever that offset is. So for us, we're only dealing with one data type. So here we're going to pass a void pointer 0. The reason behind this is that it does not allow null pointer to be used here or null. You have to specify it this way, which is a really weird quirk of OpenGL, but nonetheless is how it works. And what this means is that the offset for our position data is going to start from here at position 0. So these are going to be the 3 bits of position data that we use. Down here, we're then going to need to enable it. So GL enable vertex attribute array 0. Technically, these can go in either order. So you can enable it, then set its information, or you can set its information, then enable it. I do it this order because this is the way that I learned from Learn OpenGL. But you can decide how to do it however you want. Lastly, just to make sure that we don't do any accidental read writes anywhere else, even though this is the only functions we're calling at the moment, I'm then going to call to GL bind buffer, GL array buffer, and 0. When you specify 0 here for vertex buffer information, all it says is that we're now using the default, which is nothing. So no buffer data will be used at this point. And then GL bind vertex array 0, so that we can ensure that the current vertex array we're using does not have any accidental operations applied to it. Of course, these 2 functions don't really need to exist in this context here, because we are only ever compiling one vertex array because we have one object we're trying to render. But when you start building a system that has more and more objects, quite often you will need to specify this so that when you next call to any function, if you're trying to change data about it during the creation process, sometimes having GL bind buffer called can cause the incorrect operation, and you don't want that to happen if you haven't unbound them already. So unbinding them at the end of every function is kind of just a good thing to do. Last little bit here, we are finally ready to get to the bit where we actually draw our triangle. So within here, the actual step of drawing something at the moment is relatively simple. All we have to do is call to GL use program on our contexts shader program. So context.shader program. And this tells us that these two shaders are the ones that we're going to use as specified before. So within here, we're then going to want to draw a specific object. And as I mentioned earlier, that is specified by its vertex array. So GL bind vertex array, context dot vertex array. And now we're going to need to draw a number of triangles. So we're going to call to GL draw arrays, GL triangles, because often OpenGL gives you the option to draw in triangles, triangle strips, lines, points, whatever you imagine you can draw it as. And in here, we're going to need to say the first in the array. So we're going to be drawing from number 0 as our first vertex. And we're going to be wanting to draw 3 triangles in total. So there's the count that we do. And then from there, we swap buffers. And in this context, once all of these operations have ended, the buffer that we're writing to, which won't be displayed by the time you do all this, has now been filled with all the information, which now means that we can call to swap buffers, which will then display everything that we want to use. So if you go here and hit Control-Shift-B, we'll see that main compiles relatively simply. And now if we hit F5, we should see that we get a triangle on our screen. And would you look at that? We do. It's a little bit stretched, maybe doesn't quite look like the triangle you would expect, but nonetheless, we now have a triangle. We can't really do anything with it. All it does do is that you can see it's orange, and we can see that all the information that we have specified, our coordinates have lined up most wonderfully. And we can quit out here and everything works. So what does this mean for us? Well, it means one very, very simple thing. We are ready to actually start writing the rest of this game engine. It's been a painfully long 12 episodes. I don't know how many months it's been. It feels like it's been about 8 months or so since I started this series, and only now have we actually gotten to the part of actually rendering a triangle. Of course, there was a fair amount of setup, and in complete honesty, we haven't used a lot of that setup to get here, but we do have a very verbose system. And of course, we have a completely platform agnostic way of doing things such as window creation and GL context creation that, if you actually look at the OpenGL code that we've written, does not use any of the things that we would usually expect to see in an OpenGL program. So what this means is that from here, we can start to move on with the series. The next episode, I haven't quite decided what I'm going to be doing, but hopefully it's something to get these shaders into their own shader files rather than existing simply as defines in a C source file. And there are, of course, other systems that we will need to write eventually. So we will see how this pans out. A very big thank you for watching and sticking through the series so far. But that's all from me, and I'll see you in the next episode. A bye.